Today's lecture is going to begin our conversation about refrigeration. And, one of the really interesting things I think about refrigeration is that as opposed to a heat engine where we were going to add energy to then do work, in a refrigeration system, we're going to do work to remove heat. And so our very first foray into refrigeration is going to talk about the Carnot refrigerator, because just like the Carnot heat engine, the Carnot refrigerator provides really a theoretical limit for the best performance that you could hope to achieve from a refrigeration system. And one of the things that I think is kind of interesting, and we'll try to draw some parallels between the two here, is that if we remember in the heat engine, we drew a TS diagram, and it was a perfect square or rectangle. It wasn't necessarily a perfect square, but it was a rectangle that existed between a hot temperature and a cold temperature. And if I were to draw the TS diagram for the Carnot refrigerator, it's going to look exactly the same. We're going to have a rectangle, and that rectangle exists between a hot temperature and a cold temperature. But in the heat engine, if you remember, the first step in that process was to compress the gas first to T hot. And so, step one in the Carnot engine, maybe I'll label these here, right? So this is the Carnot engine. This is the Carnot refrigerator. That the first step in this process was an adiabatic reversible compression from T cold to T hot. And sorry, that T is quite weird. Okay. And in our TS diagram, that was this step, right? And we called that step one. And the reason that we did this compression from T cold to T hot, was then we were going to theoretically move our system to be in contact with T hot, right? So we were going to take in heat into the system from the surroundings in that step, right? And so that second step is a reversible isothermal expansion at T hot, right? So that was step two. And when we looked at this, right, we called that sort of Q in, right? And the whole idea then in an engine is that you sort of prep the system, you accept heat, so that way in the very next step, we can do work, right? And so step three is like the work step, where we're going to do an adiabatic reversible expansion, right? And it starts at T hot and ends at T cold, right? So we're here, right? And that's step three. And that is where we get the work out that we're interested in. So in the engine, this is like work in, Q in, work out. And then the final step in the heat engine, of course, then was getting back to our initial state, which was an isothermal compression at T cold, right? Okay, and that's step four, right? And we're going clockwise around this engine. But let's think about really the difference in what we're trying to do between the engine and the refrigerator from a heat perspective, right? So from a heat perspective, we want to take in heat at the highest temperature in the heat engine. But in a refrigerator, that's not true. If we think about the refrigeration, like let's just take the refrigerator in your house, the high temperature in the cycle is just the room temperature in the room. But where your system is going to accept heat is at T cold. And that's a difference maybe in perspective, and you might not have thought about it like that before, that in a refrigeration cycle you take in heat at the cold temperature because the system is not the refrigerator, right? The system is the fluid that is being pumped around the cycle, right? The actual food and the refrigerator compartment in a refrigerator is not the system, it's the surroundings. And one of the things that I'd really like you to try to do as we work through refrigeration problems is really start to think of it that way, that the space in the refrigerator is the surroundings. It's not the system. Even though my orange juice I usually think of as the system, but that's not true. So if we want the surroundings to be at as cold of a temperature as it can be, that means that we have to take in heat at the cold temperature. And that's what our system does. So here in a refrigerator is actually Q in. And that step is, if you're going to take in heat, it has to be an expansion, right? And if it's going to be isothermal, right? So you have to do a reversible isothermal expansion at T cold. And I'm actually going to start the cycle just talking about that, and I'll call that 2 star. That is a reversible isothermal expansion at T cold. So that is step 2 star. And we're going this way on the diagram, right? So we're actually moving counterclockwise. Now, to prep our system to do that, first we had to do a reversible adiabatic expansion from T hot to T cold, right? So this side of the refrigerator is step 1 star, right, for the refrigerator. Then step 3 in the Carnot Refrigerator, now we have to get back to T hot. So again, we're going to do a compression. So this is a reversible adiabatic compression from T hot, from T cold to T hot, right? So that's 3 star. And we went to here. And the 4th step in the refrigeration process is that we are going to do an isothermal compression. Of course, it's also reversible at T hot. Okay, and so this is 4 star and going in that direction. And so if we want to think about this from the perspective of work and heat, well, Q in, right, we're accepting heat into the system in step 2. In step 4, we're rejecting heat to the surroundings, which in your house, right, these would be the coils, right? Q in here would be the coils in your refrigerator. And Q out would happen as heat is rejected to to the room, right? So you've probably been next to the exhaust of a refrigerator, right? There's a fan that blows over a heat exchanger, and if you stand next to, usually it's the back of the refrigerator, sometimes it's the side, but it's warm, and so you're rejecting heat at the room temperature, accepting it at the coil temperature. And now in this process, we did a compression here in step 3, right? So this is work in, and then an expansion is done in step 1. So that is work out. Okay. So, one of the real differences, like I said here, is how you think about heat in a refrigeration cycle. And it's going to take probably a little bit as we do this example or this type of system, solve a couple of example problems. And then as we move into other refrigeration cycles, it would really help a lot, I think, to understand what's going on by remembering what the system is, right? And I can't emphasize that point enough. All right, so that's, if I had to point out 2 weird things about refrigeration cycles, the first one is that Q in happens at the cold temperature, right? Kind of weird. Okay, so before I move on, does anybody have questions about this or the corollary between the refrigeration cycle and the engine cycle?
I guess not.
Okay, yeah, I was actually going to flip over and make sure you guys are still there. Okay, so hopefully that's clear. But one of the obvious questions when you start to deal with a new system is that we've talked a lot in our class about efficiency of cycles. And so what is the efficiency then of a refrigeration cycle? Well, it turns out that when we've wanted to talk about efficiency in the past, right, that's always been minus the net amount of work that's done over the heat that you've added to the system. Well, if that's the definition of efficiency, that doesn't make any sense at all for a refrigerator, right? Because the idea is not to add heat and to do work. In fact, it's to do the opposite, right? It's to be able to absorb heat at the lower temperature while doing some amount of work. And so if we wanted to define this figure of metric as something like heat absorbed at the lower temperature, right? Or maybe I'll just say at T cold, divided by the net work that's performed. Well, that's actually defined as the coefficient of performance. And that's given this symbol, it's like a script W. And to not confuse it with work or any of the other things, I also like to put a line underneath it, right? And this thing is the coefficient of performance. Okay. And so if that's true, then for our Carnot refrigerator, that the coefficient of performance is then equal to the heat that's absorbed. So remember, that was done, if we just sort of scroll back here for a second, that was done at step 2, right? So this is like the heat that is taken into our system at 2 star divided by the net amount of work. Well, remember, we've said this a couple times, that delta U for a cycle equals 0, and that is equal to the sum of the heat steps plus the sum of the work steps. And if that's true, then the net amount of work that is performed is just equal to minus the sum of the Q's, or minus Q2 star plus Q4 star, right? And so then that makes this minus Q2 star minus Q4 star, okay? And for those individual steps, right, 2 and 4, we have a reversible isothermal expansion or a reversible isothermal compression. And so if you remember our entropy balance, right, is that the generated entropy is equal to delta S of our system minus Q over T surroundings. Well, remember, these steps are reversible. And therefore, what that means is that the heat in any one of those steps just equals T surroundings times delta S. And so that means that our coefficient of performance here is just the cold temperature times the change in the entropy in stage 2 star divided by minus T cold times delta S 2 star minus T hot times delta S 4 star. Okay, maybe I'll extend this out a little bit. And if you look at our TS diagram, because steps 1 and 3 are reversible and adiabatic or isentropic, we know that delta S4 actually equals minus delta S for step 2. And if that's true, then our coefficient of performance for this Carnot refrigerator becomes equal to T cold times delta S in stage 2 divided by minus T cold delta S 2 star plus T hot times delta S 2 star. Or we come up with this expression that the coefficient of performance equals T cold divided by T hot minus T cold. Okay. So then the next thing I'd like to ask you guys are, what are the bounds of the coefficient of performance? So we know that the bounds on the efficiency is that the efficiency has to be less than or equal to 1, right? But what are the bounds for the coefficient of performance?
Would it be the opposite?
What would you mean by the opposite?
They'd have to be greater than 1?
I'd say greater than or equal to 0.
All right, anybody else?
It's gotta be greater than 1, because TH is bigger than TC always, so it's gotta be bigger than the difference.
So with regards to being greater than or equal to 0, I think here, let's do this. So efficiency is bound by 1 and 0, right? Right, the efficiency can't be less than 0. The coefficient of performance, you are correct that the coefficient of performance is always going to be greater than or equal to 0, because if you think about the extremes, if T hot just got really big relative to T cold, you would get to something like, 1 over a huge number, which is approximately 0, right? So you are correct that that has to be greater. Actually, I don't even know if you have to say equal. It really has to just be greater than 0. So it has to be greater than 0. But what does it have to be less than? Anybody?
It doesn't.
It
It
doesn't.
doesn't?
That is correct. In fact, look at what happens here. That as T hot and T cold become closer and closer and closer to each other, the refrigeration system actually performs better and better and better. And this is one of the reasons why, if you think about places in the United States where heat pumps, which are basically just Carnot refrigerators, are very, very popular. It's in temperate climates like the Pacific Northwest or New England. Or there are parts of like Minnesota and Wisconsin. They're in those types of places. Heat pumps are extremely common because they're very efficient when you have small differences in the temperature. Whereas in a place like South Carolina, where it's 4 million degrees in the summertime, a heat pump is really not a smart investment most of the time. And so another consequence to this, though, is that if the coefficient of performance is the heat that you removed over the work in, that also means that the amount of heat that you can absorb is greater than the amount of work that you have to do, generally. If you have a very bad system, this doesn't have to be true. But this is like weird thing number 2 for refrigeration cycles, right? The first one was just getting your head wrapped around the fact that heat enters the system at the low temperature. And the second one is that you're often able to do more work, to extract more heat than the work that you put in, which kind of makes it feel like you're getting a free lunch, but that is not the case. And so that's sort of weird thing about refrigeration cycles, number 2. And in fact, coefficient of performance, between like 4 and 10 are pretty normal. If you were to actually look at some designed systems, and we will actually, when we move past the Carnot refrigerator, calculate a lot of coefficients of performance, and you'll see that they're certainly greater than 1. Okay, so kind of an interesting thing. So if everybody's comfortable with this, let's move on and solve a couple of more basic problems. And then what we're going to do is I'm going to give a problem that I want you guys to work on between like today and tomorrow. And I'm going to give you guys another chance to like get 5 points of homework extra credit. And I did this once before. So I'll give the problem statement, and then we'll end class. And we'll end class a little early, so that way you guys can work on it even while class is going on. And then you can turn in your solution by tomorrow at 5 o'clock. And then I will post the solution on YouTube to the problem after 5 p.m. tomorrow. So that way you guys can then watch it. Okay, so it's just another chance for you guys to earn a little bit of extra credit. Okay. All right, so let's do this first. Let's solve a couple of the more straightforward problems, and then we'll just introduce the other problem and then give you guys an opportunity to work on it. Okay, so here's the first problem that we'll solve today. It says, according to the owner's manual of your refrigerator, the coils are designed to operate at 10 degrees Fahrenheit. If the temperature in the kitchen is a constant 72 degrees Fahrenheit, what is the maximum amount of heat that can be removed per joule of work done. We're told in this problem that the cold temperature is equal to 10 degrees Fahrenheit and the hot temperature is equal to 72 degrees Fahrenheit. Now, at the very beginning of our semester, I said I have a preferred set of units that I like to work in. And of course, you could take Fahrenheit and convert it to Rankine. And this would be absolutely fine. You could solve the problem the same way, but I prefer to convert to Celsius and then to Kelvin. And so 10 degrees Fahrenheit, if you do this conversion, is 260.9 degrees Kelvin. And 72 degrees Fahrenheit is 295.4 Kelvin. Okay. And so our coefficient of performance then for this problem is then equal to, right, T cold over T hot minus T cold, which is 260.93 Kelvin divided by 295.37 Kelvin minus 260.93 Kelvin. And of course, then putting that into calculator, that is a coefficient of performance that's equal to 7.6. Okay. And now the problem asked, right, what is the maximum amount of heat that can be removed per joule of work that's done? And so remember, the definition for our coefficient of performance was the heat that we could absorb divided by the net amount of work that we were doing. And so in this case, then we're after the amount of heat that can be removed. So then Qn just equals the coefficient of performance times the net amount of work that can be done. And now you can see why I put the line under the W, so it doesn't look like WW net. And then that's equal to 7.6 times per joule, right? 1 joule. And so then Qn is equal to 7.6 joules, right? So we can take in 7.6 joules for every joule of work that we do. Another way that you could ask essentially the same problem is to say, well, if the temperature in the kitchen has that temperature, right, and the coils are still at 10 degrees Fahrenheit, what is the power required to remove heat at this constant rate? And we're really just going to use the same piece of information that we did, right, and the same equation, except now we're just going to convert that equation to give us the net amount of work is just equal to the rate that we are removing heat from the system divided by the coefficient of performance. And so the problem said that was 11 kilojoules per second divided by 7.6. And that's equal to 1.45 kilowatts. And there are other, hiccups to problems like these that you could add as well. They're little wrinkles where you could say, given that the electrical cost in your area is 11.5 cents per kilowatt hour, how much would you spend to run your refrigerator for a year, right? That's another way that we could solve a problem just like this. I didn't actually solve that problem. And so instead of pulling out a calculator and everything, but just to let you know, there's little simple questions that can be asked and all sorts of little wrinkles that can be put in problems like that. Which, if this is okay with everybody, kind of brings me to the third problem and the one that I'm going to open to you guys for extra credit. And that problem says that you live in a place where weather extremes are uncommon. So instead of buying a furnace and air conditioner system, you design a simple reversible system where the house exchanges heat with the constant temperature earth about 40 feet below your house. So you would like a year-round indoor temperature of 25 degrees C, and the underground temperature is 15 degrees C. If the system runs on electricity, calculate your average monthly electric bill for a summer and winter month if the average cooling requirement in the summer is 50 kilowatts and the average winter heating requirement is 40 kilowatts. Okay. And if you can, go ahead and grab a screenshot so you definitely have the problem. I'll also send an email through Blackboard to everybody so you have the problem statement as soon as we sign off here. And as you guys start to work through this problem, I want you to remember a couple of things. So remember that, first of all, a refrigerator, right? The system accepts heat at T cold and rejects it at T hot. Right? That goes all the way back to this diagram here, right? So the bottom here, right? You take in heat at T cold, you reject it at T hot. In a heat engine, that you reject heat at T cold and you accept heat at T hot. Okay, so just think about that a little bit, because obviously a reversible system, in the winter, we're going to run the system in one mode, and in the summer, we're going to run it in the other mode. Okay. The other thing to keep in mind as you work to solve this problem is, as you, of course, find the efficiencies of the process, you'll also then have to determine, right, this 50 kilowatt in the summer, 40 kilowatt in the summer, in the cycle, is that Q in? Is that Q out? And then how do I relate that to efficiency or the coefficient of performance? And then the work, right? The net amount of work. Okay. So hopefully, the problem's going to make some kind of sense. Like I said, I'm going to leave this as an open question for extra credit. You guys turn in whatever you got by 5 o'clock tomorrow. And then just after that, I will post the solution as its own standalone video on YouTube.